Hi everyone, today we're going to be talking about topic 3.7, solutions and mixtures. So we're going to be moving away now from talking mostly about gases, and we're going to talk more about chemistry and solutions. And so what we have to remember about solutions is that these are homogeneous or homogeneous mixtures of two or more substances. Few terms to remember: the solute is the substance being dissolved, and the solvent is the liquid dissolving the solute. Another important point to remember here is that in a solution, the solute is uniformly dispersed in the solvent. Right, and so there aren't areas where the solute is more concentrated than in other areas. It's uniformly dispersed throughout the entire solvent, like in this image right here. The ability to form a solution depends both on just a natural tendency to mix, and we'll talk about kind of some things that affect that. And the other one, which we've learned quite a lot about, are IMFs, right? Stronger IMFs mean things like to be in solution more rather than separated from each other. Few properties of liquids solutions that we need to remember are that components cannot be separated by filtration. Right, and so if you have kind of a precipitate in there, that can be separated by filtration, but the solution itself, everything that's dissolved in the solution, cannot be separated by filtration. There are no components large enough to scatter light. And this is going to be really important kind of later on when we're thinking about some spectroscopy that you can do with solutions. Components can be separated, however, by what's known as distillation and chromatography, which we'll be talking a little bit more about in a future topic, but just so we know ahead of time, right, these components can be separated by these two techniques right here. Now, something that's sort of related to solutions, but isn't necessarily a solution, is known as a colloidal suspension, and these can scatter rays of light. And so a colloidal suspension, if we kind of have this solution here, you have, a liquid dissolved in here, so some sort of liquid, and we have these bigger particles in it, which are kind of dissolved, but they aren't necessarily, fully dissolved like you would think like a salt. And so if light comes in, I'm going to draw this in red, if a ray of light comes in and hits one of these, it's going to bounce off and scatter. And so if you look at this image right here on the left, we have a solution, right? Light passes right through it. But on the right here, you can see that there's an area in the middle where light is scattering. And so this would be a colloid. Right, and so there might be some questions on exams thinking about colloids, and colloids are essentially they're suspensions of some sort of a solute in a solvent. So you have these bigger particles in it rather than small dissolved ions in a solution, for example. So there are a lot of different ways that we can think about the concentration of a solution, and a lot of different ways to measure it. The most common way that we think about is molarity, which molarity, as we know, is defined as moles of our solute, right, what is dissolved in the solution, over the liters of solution. And sometimes you might see this written as M, right? Uppercase M is molarity, is equal to N, number of moles of solute, over liters of solution. right? So it's N over L or it's N over V, right? Number of moles over volume, specifically moles over liter. Now, when we're thinking about solutions, there's some really important stoichiometry that we always have to remember. The first thing to remember is that ionic compounds dissociate into ions when they're in solution. So if I have, right, some solid sodium chloride, I add that to water, right? So I'm going to say dissolve in H2O. In solution, I'm going to have sodium plus ions, and now these are aqueous because they're dissolved, plus Cl minus ions, which again are aqueous because they're dissolved in solution. But if I have something like calcium chloride, right, CaCl2, that's a solid, same thing, I dissolve in H2O. I'm not necessarily reacting it, right, which is why I'm just writing dissolve in H2O. I'll still have calcium 2 plus ions in solution. But in this case, right, it's CaCl2, I should have 2 Cl minus in aqueous solution. So the important thing to remember here is that the concentration of the original, or, you know, in this case, CaCl2, is not always the same as the ions. Right, so here, if we have, for example, you know, 1 molar calcium chloride, in our product we would have 2 molar, right, because we have 2 chloride ions. Okay, so here's just a little bit of an example of thinking about, you know, solutions and some problems with solutions. And so we have here this question saying if the value of silver ions, Ag+, is 7.1 times 10 to the minus 7th molar, calculate the minimum volume of distilled water, specifically in liters, needed to completely dissolve a 5.0 gram sample of AgBr at 298 Kelvin. And we're also given the molecular weight of AgBr, which is 188 grams per mole. Okay, so in this case, we're given the mass of AgBr and we're given its molecular weight. So the first thing we should really think about doing is just calculating the number of moles, right? We're thinking about solutions. We're thinking about molarity. That's moles over liter. We ought to calculate the number of moles. And so it's going to be 5.0 grams of AgBr divided by 188 grams per mole. Our answer there should be 0.0266 moles of AgBr. Of course, in this case, I'm not going to round my sig figs just yet. And if I want volume, I need to think about my molarity calculation. And so molarity is going to equal number of moles of solute over the liters of solvent, also known as V. And so if I want to solve for V, what I need to do is divide the number of moles of solute by my molarity, which is also given to me right here. So if I want the minimum volume of distilled water to dissolve my AgBr sample to get silver ions, all I need to do is do V is equal to our number of moles of solute, which is 0.0266 moles AgBr. Divide that by the molarity, which is 7.1 times 10 to the minus 7, right? And it's molarity, so we should have moles per liter. So I'm going to do moles over times liter minus 1. You'll see the moles are going to cancel out, and we should be left with liters. And the answer here is 3.7 times 10 to the 4th liters, right? And this is also, if we look at our numbers here, we're given 5.0, we're given 7.1 and 188. This should be 2 sig figs, and so my answer should be reported like that. We'll be going over some more practice in class, but for now, that's all. Thanks, guys.